Okay, I will start the practical session. Hi, this is the last practical session of this lecture. I'm Tae-Yeon-Suk Won, and today I will cover three topics. First one is implement and train clip, and then we use pre-trained clip for zero-shot prediction task. And then lastly, we will cover stable diffusion training with classifier-free guidance diffusion. Okay, let's start the practical session. Okay. First, install the package for the cover the practical session. Before start the practical session, you have to change your runtime code with GPU. Okay, and then import the library and the PY file for the tokenizer. So implement this PY files and library. Okay. Good. And then import this tokenizer. And we will implement clip and download the Frisker AK dataset. We will use this dataset for implement and training the clip. And this is the dataset labeled consisting 8,000 photos with 5 captions for each photos. It includes image obtained from this website. And so I will show that data set. This is the image of the data set, and it contains 5 captions. So the image contains like first one is a child in a pink dress is climbing up a set of stairs in an entryway, and a girl going to a wooden building, little girl climbing in a wooden playhouse, a little girl climbing a stair to the playhouse, a little girl climbing the stairs to her playhouse. This is the data set, and this is a caption. So we will going to download the data set with this codes, and after you download the data set, unzip the data set, this one and this one. Okay, this is the pre-process of data set. And then this code is make a data loader for train data loader and dev data loader and test data loader. I think this is familiar code, so I will skip. Okay, and let's implement the clip. As I prepared the image of the clip. So in this session, we will implement text encoder and image encoder and the cosine similarity of the matrix. So text encoder is a functions by covering texture input and into a numerical representations, allowing the model to understand and related text to image. So this encoder is trained on the vast array of internet text and image pairs. enable it to recognize a wide range of concepts and relate them to visual contents effectively. So this is the code for the text encoder, and I give you the text encoder class like this. And I want you to generate this for function, and I will give you 5 minutes. After 5 minutes, let's check together how this code works. Okay, let's see the codes together. Okay. This is the function for initialized parameter. I think this is the crucial function for setting the initial weights of the models which can significantly impact the model's learning and the performance. So we will use normalization, this normal distribution with a small standard deviation with small standard deviation. Okay. If you want to see the more detail of this code, please see the document of OpenAI GitHub of Clip. And let's see this fourth function together. This is the input. The input text is assumed to be the tokenized when past the token embedding layer, and each token into the fixed size vector like batch size by sequence length by transformer width. And after the tokenizer text embedding the text, we will get the X. This X goes to the position embedding function. By this code, we can positional embedding for add information about the position of each tokens. And then we arrange the data to suit the transformer model. So it requires the input format as sequence length by batch size by transformer width. So this is how we get like this tensor size by pyramid function. And we encode the data input text to the transformers. And then after passing through the transformer encoder, the dimensions are permitted back to the original form as batch size by sequence length by transformer like this original. We can permute like this and get the original size. And find the last tokens in each input sequence and select only the output of the token. I don't know what this means in final. And then lastly and finally, we select the last tokens and we projection into the another embedding space. Yeah, just it is okay to do like this. And select the tokens output is projected into another embedding space, and this is typically used to adjust output dimension of the model. And then how we implement this text encoder like this. I think you can easily implement text encoder because we do a lot of practical session. We do a lot. And let's import the image encoder. This excels in understanding image in the context of the natural language description. Unlike the traditional models that require specific training for each task, ClipCat is versatile and can handle various tasks without task diffusion training. So it learns from various range of internet image and their associated text, enabling it to understand and categorize image in a way that aligns closely with human perception. So Clip's approach allows it to perform well across broad spectrum of visual tasks, including object recognition and complex reasoning with about images. So I give you some image encoder class code, and I will give you 5 minutes to implement this for function. In this function, you have to use this in pre and in post. Okay, after 5 minutes, let's check together. After practical session, if you have any question, please okay. If you have after this practical session, if you have any questions about this code, in the front of this IPython code, I written my email. So feel free to ask any questions by my email. Okay, let's see the image encoder together. This is the same as the code from text encoder, and the code for image encoder is like this. Let's see together. First, apply 2D convolution layer to the input tensor X, and the shape goes like the batch size by width by grade by grade. So the batch size is the number of image, and width is the number of outputs and channels from convolution. I think this is wrong channel. And width is the number of the output. And we're going to flatten the grid to create sequence of patches. The shape becomes batch size by width by number of patches. And this is the total number of patches. So, and then we will transpose second and third dimension to implement the tensor for the transform encoder. And the shapes goes like this. And we will expand the class embedding because we have to create image embedding for each image in the in the batch with the shape of batch size by 1 by width. And then we concatenate class embeddings to the beginning of each sequence of image patch. This step is crucial for model to learn global image representation. And then we have to add positional embedding, to the X, and then apply layer normalization before feeding the data into the transformers. And we have to send the data to the transformer encoder. And before sending the transformer encoder, we have to permit for the encoding the transformer. So the function goes like this. And then last, we have to apply the last layer normalizations in this code, like in post. Finally, we pass this representation through the final linear layer. So we can get the X, and this is the image layer functions. And okay. And then the important part of clip is this part. This can learn the pair of text and image. So the contrastive loss in clip helps the model to learn by comparing pairs of image and text. It rewards the model with correctly matches an image which is corresponding the text. So and by this contrastive learning, it penalizes for incorrect matches, and this approach is effectively align the representations of image and the text in the sharing the embedding space. So I will give you 5 minutes to implement this contrastive code, and after 5 minutes, let's check how to implement the contrastive loss and what is the contrastive loss. So after 5 minutes, let's check together. Okay, let's check together. First, we'll have to do this. We will need the temperature. Is the parameter is just the softmax probability distribution tuning like difficulty of learning process. Okay, and first we have to normalize to using L2 normalization with f dot normalization function, and this normalization stabilize the cosine similarity calculation between two features of image and the text features. And then after normalize the image feature and text feature, we have to memo to compute image feature vectors to and the transpose of text features. And this representation is the cosine similarity between the image and the text. And then we have to generate labels corresponding the diagonal elements indicating each image matches with the corresponding text. And then we have to do the cross entropy loads for the image and text to image. So by using f dot cross entropy, this cross entropy loads for image to text, this is this one, and text to image, matching is calculated, and this increases the model to the corresponding match image and text pair, and by this loss we can get this loss calculate by return. And this is the model of the clip I will give you. This is the optional. If you want to do the initial parameter, you have to select this. If you do not want to do it, you can skip this one. This is the config, and this is just parameters. So if you want to change whatever you want, or this is not the same as the clip paper, because this is collab environment is too small, so I change it, but you can change whatever you want and practice in the collab or your own servers. And then we will train this, but I think you're familiar with the train, and there is a lot of practical sessions to cover. So in this time, we will skip the train and eval code. Okay. The important thing of Cliff is this model can do the zero-shot prediction. So this sections we will cover the zero-shot image classification. And this session for zero-shot prediction, we will use Cypher dataset, Cypher 100 dataset. So I explained this zero-shot prediction very briefly. Clip version detection is advanced AI technique that enable models to understand and identify object in image without prior specific train on those objects. So it combines natural language process and computer vision, utilizing a large-scale data set of image and text to learn visual concept directly from language description. This approach is significantly expand the model's ability to recognize a wide variety of objects and scenes, and it can leverage language description to interpret image it has never seen before. So zero-shot detection in clip is particularly powerful because it bypasses the need of extensive label data set and making it versatile and efficient for diverse applications. These methods demonstrate a remarkable understanding of both language and visual content, bridging the gap between the textual and visual understanding in AI. So this section, we will cover zero-shot image classification, And in this section, we will use Cypher-100 dataset. So first, you have to load the model. And then we will going to process the text and image by this. And we will use the clip tokenizer. And when we use clip tokenize, we will get the tensor like this. And okay, after pre-processing the text image, we are going to feed 8 examples to image in the text description to the model and compare the similarity between the corresponding feature. And we will see how the cosine similarity works with image and text pair. Okay. So this is the description, and by the dictionary, the page images description is a page of text about segmentation, and this description of announcement is a portrait of announcement with American flag, and rocket image is a rocket standing the launch pad. This is the description we will need, and by this code, we will append the images to the original image list, and the keeping the original data is important for preserving the unaltered state of the image for reference or comparison, and the list for the image for the processed image, and append the text of this description. And then we're going to build a feature. We normalize the image and tokenize each text input and run forward paths of the model to get the image and the text features. So by forward path, we can get the image feature and the text feature with the encode text function. And then we normalize the text and image features and calculate this with the dot product and get the similarity score. By this, and let's see how the calculating cosine similarity works together. Okay, this is the result of these code blocks, and let's see together. In zero shot prediction, I will explain just this implement code. Without, I will give you some time because of time issues. And as you see in this picture, you can see that you can see this man looking in a camera, and the description of person looking at the camera on tripod. This description has the most high similarity comparing the other image data. And as you see like this, a black and white still house of horse. This description is highest similarity score with this image. So by seeing this figure of contrastive learning metrics, you can see this clip can figure the text and image hair. Okay, and let's do the zero shot image classification together. By this code, you can classify image using the cosine similarities and the logic of softmax operation. So like this, you have, oh my gosh. Okay, you can see the cosine similarity with this. And first, you have to download the Decipher-100 dataset and transform it with the clip preprocess functions. And we will make descriptions like this, as you see in the picture, a photo of object like this. So we'll make the cost, we do this description like this photo of label in the Decipher-100 dataset. And after making description of this, we encode it to the tokenizer function and get the clip tokenizing of the test description. And then we put this test token to the model and get the feature of the text and normalize it. And then next transpose this text feature and dot product with the image and get the text probability and get the top probability of text with the pair of the image. And as you see in this picture, the clip can do well zero shot with this one. And like this is the photo of man, and the clip can clip to the highest probability on the label to the man. And this is the image of motorcycle. So the zero shot clip can do the highest probability on the motorcycle comparing with bicycle or lion motor, pickup trucks, and swift peppers. And this is the Austrian of image. So this is the image of human instrument. So the clip model scores highest probably on the human labels in the Decipher-100 dataset. Okay, this is all of the clip, and if you have another questions about this code or how to implement, just feel free to send me an email. And we will do the classifier-free guidance. We will cover classifier-free guidance training. So in this note, we will going to implement the stable diffusion and inference with classifier diffusion. And so we will training a class conditioned, sorry. I'm sorry. And I will keep the practical session. So by this class condition diffusion, we will train the class condition diffusion model with the MNIST data set, and we can specify which digit we would like to model to generate at the inference time. So let's start the code. First, for training class condition diffusion, you have to implement this PIP install diffusers in the Colab. And you don't have to implement this because we do not use this one. And for this, you have to implement this one. And then we update to the device, upload to the device, and download the data set and make a train data loader. Oh my gosh. And this is the image of the data set, and the size of data set is 8 by 1 by 28 by 24.8. And let's creating a class condition unit. For this, we create the class conditioned unit with some additional input channels and map the class label to learn the shape of class embedding size. And then concatenate this, and I'll give you this conditioned unit class. And for the text encoding, in this practical session, I will use this Google Bird Encased pre-trained model. This is a 2-layer transformer model, and I think this is the same as initialized BERT model. And I want you to generate this encode label with cliff function. We have to, in this session, we will cover text to image task. So we have to implement this code like if this code. And this is the class conditioned unit. So 10% of layer comes the null, and 90% of layer come the true label. So when the label is null, we have to do like this, and when we do the specific label comes to this function, we have to make this, and we're going to utilize BERT tokenizer and text encoding with BERT and get the return of the function. I will give you 5 minutes to do it, and after 5 minutes, let's check together. Let's check all the codes for this one. I think someone do well. I'll give it more 2 minutes more and let's check all the code together. Okay, let's implement code together. I will do it together for this code. For the classifier-free guidance and the valid label goes like f dot photo. We will give label to this function. So a photo of like digits. It can change whatever you want, a photo of label or whatever you want. If label is not null or for labels. And we can tokenize the valid labels and paddings to max. I will erase this because, and max length is 77. This truncation. Padding. I'll give true and return tensors. We can tokenize the text. And we will load the device like this. You can change the code whatever you want, but now I will do like what's this one? The device self.text encoder device 4K and what? I'll change this input item. It's like this. So, and then we will get outputs like self.text and to asterisk inputs to pass the initialized port text encoder and the class conditioner output gonna be outputs dot last hidden state and get the last hidden state, and this is gonna be the return. Okay, I think everyone follows this code. And then I will explain these four functions. First one, we can encode, we will convert the class labeling. We will get the X shape like this. And by this function, as we implement before, we will get like valid labels of, and the tokenizer comes out and get the last hidden state of BERT transformers, and this is gonna be the class count, and get the CLS token by this code. Because we will use CLS token for get the representation of the text encoding, and then transform and the embedding like this, and then we will get the class con, and embeddings are concatenate with the original image X along the channel dimension. This step is efficiently combines the information from the inputs and the class conditioned image. And then finally, concatenate input. This concatenate input pass the model and the time step of, and generate and pass the unit. About this, I think we will cover the last session, DDPM. So I will move on. And by use DDPM scheduler with the 100 time step, and by this code, we can train the class conditioned unit, but I think this is easy, so I will skip the code. But I will explain some important thing for training. First, this one. In this session, when the label come null, 10% of label come null, we will do null. But if 90% label is the specific label, we will do like a photo of the digits its label. So this is the code that made 10% is null and 90% is specific class for the conditioned unit training, conditioned unit. And then by this condition unit and the noise image from this one and the time step to the net and get the prediction, and we will get a loss function with this and the train with the 10 output. So for the time issue, I will skip this all the training codes, like it consumes a long time. And after we finish training, we have to inference with free guidance, and this is very important to give guidance to generate a very better image. This is a formula of the guidance, and I will give you 5 minutes to implement this formula, and let's check the codes together. I will give 5 minutes to implement this code. Oh yeah, I think some of one already finished well. And let's implement together. And before implement the guidance laws, guidance formula, and explain some codes. This is a set of guidance scale, which is hyperparameter, and you can do like more than one. And we will use this classifier-free guidance to control how much to the conditioned model and the condition model output. So it influenced the output, final output, and by this X, we create a tensor X with random noise of shape 8 by 1 by 28 by 28. It's 80 samples and one channel 28 by 28 pixels each, and move it to the specific device to the GPU. And then this line is create a fluorescent tensor for the Y concatenate class labels. Each class label from 0 to 9 and it is represent 8 times to make 18 labels in total. So this is also the tensor moved to the specific device like this. And then this is a sampling loop. We will use the time step for 1000, and the larger time step make the more good image. So no a lot of study use like 100 to 150 for the time steps, I think. So to make the XYT to the unconditioned image and a conditioned image, and do like X and time step and this null by X the shape 0 for the conditioned unconditioned image with a null. And we will calculate this function to here, and the guided noise we will implement, and this is guidance noise for unpret plus guidance scale and multiply with noise guys unpret text, this conditional prediction, and minus this unconditional prediction, and we get the guidance noise. And by this we will update the sampling, and by this code we will implement the code. I will show you how it works after training. You will get the output like this is the output like this one. I want you to recommend to do without this guidance. When you do the guidance, you will generate the more clear image that corresponding with text like where is it, like photo of digit label. Okay, and this is the output of the classifier guidance, free guidance inference. So okay, this is all of the lecture practical session. I will wait 2 minutes, and after 2 minutes I will end up the Zoom. Okay, it is over. You can go out if you want. Okay. Okay, I will show you guidance noise code. This is the formula of apply guidance code. See, I will show you 1 minute more. Okay. I think we will stop the lecture. Bye.